All right, hello again, everybody. We're going to look at question 3 from TD2 problem set, which is an extension of the Borrow-Gordon, and it's also going to be an exercise in writing our own models, extending models that we're studying in new ways. So we begin with reading the question, I guess. We modify the bank's utility function. Okay, oh, and I didn't write down the old ones, so let's quickly remember, where do we begin? We begin with the production function, which is y equals yn plus a, surprise inflation, so pi minus expected pi, plus epsilon. We had the household, which was the negative 1/2 of the quadratic loss, expected pi minus pi, because they want to guess correctly. And then the old CB function was lambda y minus 1/2 pi squared, because the bank's inflation target is 0. Okay. So it says, now the central bank, instead of desiring unlimited growth, remember this term implied the bank wants unlimited growth because it's a line, right, with slope of lambda, and the maximum value is infinity, plus infinity. Instead of this, it wants to have a target k. Okay, so we want a utility function so that k is the maximum value. It wants us to rewrite the utility function to incorporate k. So right away, we should be thinking about, how can we have a target? Well, the household has a target. Their target is pi, right? And the household has this quadratic utility. So that's a great way to go. We can just make a quadratic utility function. So UCB equals, now lambda y minus k minus 1/2 lambda squared. But we have a problem here. This is a square. Okay. We have a problem here because this is positive, right? So if we maximize this, so right now this is like an upward parabola. So it looks something like this. Here's k, and it's like, it's a parabola. But it's upward facing, so if we maximize it, we're still going to plus infinity. What this is actually saying is the bank wants to be away from k, so we need to make it negative. Not a very convincing negative, so I'm going to make it negative. Okay. And then it says, make sure the function is continuous and differentiable everywhere. Perfect. Our function is differentiable and continuous everywhere. Maybe you thought about absolute value. You thought, well, we could write minus lambda, absolute value, y minus k, absolute value, minus 1/2 pi squared. This is almost nice, but when we go to maximize it, when we go to maximize this with respect to pi and y, how do you take the derivative of the absolute value, right? You would have to do maybe, I don't know. You can figure something out, but the absolute value, remember, it's like a v. So here's k. It would look like a v. And at the point k, there's no derivative because it's a right angle. So that's not allowed, and so we don't want to use absolute values in these sorts of targeted loss functions. It's much nicer to use a quadratic. It's also more numerically stable if you're interested in programming like a computer to find a minimum. A quadratic does better than the absolute value. Okay, so we have this, and then it also says, this little comment at the end, it says, finally throw in something nice to make it a bit easier to solve. What is it talking about? It's talking about what we discussed in a previous video about why is there a 1/2 here. And remember, it's so that when we take the chain rule, the 2 will cancel with the 1/2. But the maximum doesn't change. So we can actually just write lambda over 2 here, and everything's hunky-dory. Everything's the same because it'll just cancel with this and the maximum. So it's negative now. So here's our new function. And the maximum is still right here at k. Okay, great. One other thing to sort of know is that the maximum of a negated function is the same as, okay, that wasn't helpful. If we take max x squared, okay, this is the same thing as min x minus x squared. Yeah. So we can actually get rid of these minus signs by defining a new function, which we'll call the loss function. We'll call it v, and v will be minus UCB. And then now v will be lambda over 2 y minus k squared plus 1/2 lambda squared. This is another optimization trick, right? We had u, looks like this. Yeah. Now we have v that looks like this, and they share the point k. And you can see that the minimum of v is k and the maximum of u is k. But here we don't have to worry about minus signs. So we'll just have to change our problem from a maximization to a minimization, and we get the exact same answer. Yeah, nothing else to worry about. So now we're going to minimize with respect to y and pi, our v function. Oh, and this is part B, so we're done. This was our answer for part A. Great. Okay, so now we're minimizing this with respect to VCB, which is equal to our function here, lambda over 2 y minus k squared plus 1/2 pi, subject to the production function, which is, it says it's unchanged from the question 2. Y equals yn plus a pi minus expected pi plus epsilon. Once again, we can eliminate a variable. We can eliminate one of the choice variables y in this case, because y is a function of pi. You plug it in, and we can only minimize with respect to pi. So we save ourselves having to set up a Lagrangian. So plug it in, we get yn plus a. Let's factor the a right now, because we're going to need to do that later. Minus expected pi, a expected pi, plus epsilon, don't forget the minus k, all squared, plus 1/2 pi. So now we're ready to take the first order condition, which is just the derivative of VCB with respect to pi, and set that equal to 0. So first things first, we take the outside function, which is the square. We bring the 2 down, it cancels with the 2. We're left with lambda times all of that stuff on the inside, yn plus a pi minus a expected pi plus epsilon minus k. And then to take the derivative of the inside, there's only one pi here, and there's an a on it, so we get an a drops out. And the second one's much easier. There's a square sign here. It is just pi, and that's equal to 0. Okay, let's get a bit more real estate up here. I don't think we need any of this anymore. Great. Change colors. So now we're going to have, we need to split out the pi's. So we'll have a lambda, and I'll keep the not pi stuff in here, yn, plus epsilon, minus a expected pi, minus k. And then pulling out the pi, we pick up another a lambda, so it'll be a squared lambda pi plus pi equals 0. And so we'll take everything that's not pi to the right-hand side, and we're going to factor out pi on the left-hand side. So we get 1 plus a squared lambda pi equals. We'll take this over, so we'll put the minus sign in here, so we'll flip everything. So we get a lambda, and then we flip everything. So we have a expected pi plus k minus yn minus epsilon. And then divide. So we get pi equals, and this is pi star, because it's the optimum point, a lambda over 1 plus a squared lambda. And then we multiply that by a expected pi plus k minus yn plus e. And there you go. That is our optimum value of inflation. So it asks, which parameters are present in pi star now that were not present for the solution in question 2? So first we recall that the answer in question 2, so the old, we'll call it pi star L for linear, that was just a lambda. So we see that, we do have this, but then it's also scaled by 1 plus a squared lambda. And then we also have this term in here, which is like almost the production function, right? The production function is just missing a pi because we have y equals yn plus a pi minus expected inflation plus epsilon. You see, it's really close. We have yn here, we have epsilon here, and we have a e. So it's like k takes the place of pi almost, like 1 over a k. You know? So there's some kind of connection, right? It's funny. I don't have an answer for exactly what it means, but it's very, very close. Okay, anyway, so what can we say is present that wasn't present before? Well, yn is present, okay, epsilon is present, k is present, of course, we didn't have k before, and expected pi is present. So first of all, actual important things to say. Number one, the bank now thinks about the households expectations when choosing pi star. So before there's nothing to do with the households here. We got a solution that was completely independent of the household. Here now we have the expected pi shows up here, so the bank has to think a little bit about that. It also has to consider the shocks. The bank considers the shocks. So actually this pi star is a random variable. And indeed, we should probably take expectation, but I won't here because the question didn't ask us to. But yes, it's a random variable because we don't know what this epsilon is. So pi now, instead of just being one number, it's going to be a probability distribution, with some mean and some standard deviation. Okay. So that, I think, answers that. Comment on what this means for the central bank. How will the central bank use inflation as a policy tool? Yeah, I mean, they take into account these things because they care about the output being too high or too low. If it's too high, they want to change it. If it's too low, they want to change it. Before here, they just worried about getting more, always more, 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 so it was very easy. But now here, they have to think about where are we relative to the optimum that we like, and then how can we use pi to bring it towards what we like. That's why the function almost appears here, because y is embedded inside of this equation now, whereas it wasn't here before. Okay, I think that's enough for this. I will see you in the next video for part C and D and whatever comes next.